Welcome to today's explainer. When you first hear all the acronyms, the IPsec VPN handshake sounds, well, incredibly intimidating. But honestly, it is deeply fascinating once you get into it. Instead of just looking at rigid technical rules today, we're going to treat this like a high-stakes story. Imagine two complete strangers meeting in a crowded, noisy, and potentially dangerous room. They need to find a way to share top-secret information without any of the eavesdroppers catching a single word. So how exactly did they pull that off? Well, let's find out.
Okay, let's dive into this. How do two complete strangers on the internet create a perfectly secure tunnel? This is the ultimate problem we're solving today. We've got two network entities, in our case, two corporate firewalls, that have absolutely zero shared secrets. They've literally never spoken before. Yet they need to establish absolute, unbreakable trust over a completely unsecure public network, the wild, untamed internet. It's exactly like trying to pass a secret decoder ring code across a crowded football stadium where everyone is actively trying to listen in.
To put this into perspective, let's ground ourselves in a real, physical scenario. Imagine a PC sitting in a corporate office in Taipei. Now, a user on that PC desperately needs to reach a server located in the Taichung data center. But here's the major catch, right? There is no dedicated private physical wire connecting these two buildings. Between the Taipei firewall and the Taichung firewall lies nothing but the public internet. If that Taipei PC just throws its raw data out into the open, literally anyone could intercept it, read it, or even alter it. So we need to drill a secure, invisible tunnel right through that dangerous public space.
Now, because these two firewalls don't recognize each other at all, right out of the gate, they can't just start throwing sensitive data across the web hoping for the best. They have to systematically negotiate the answers to 5 critical questions before a single byte of user data can safely cross. First, who are you? Second, what specific encryption algorithm are we going to use? Third, what's our shared secret key going to be? Fourth, exactly which packets are we actually encrypting? And finally, how do I mathematically confirm you aren't some hacker impersonating my trusted partner?
To tackle those huge questions, the IP security architecture splits the workload into 2 distinct main roles. Think of it kind of like a presidential visit. First, you have IK, or Internet Key Exchange. They act like the advanced team of highly skilled diplomatic negotiators. Their whole job is management and logistics. They answer the how do we establish trust and what algorithms do we use questions. Then, once the diplomats finish their negotiations and shake hands, ESP, the encapsulating security payload, takes over. ESP is basically the heavily armed security detail that physically protects the president. In our case, it protects the actual data payload as it travels. So our story really kicks off with those diplomats, with Ike. Specifically, the first order of business is building an Ike Security Association, or IPsec. This is the initial management channel built between 2 devices to safely negotiate further security parameters. This is the absolutely crucial first step where our 2 firewalls, Taipei and Taichung, cautiously begin building their relationship. And it's vital to remember that right now, at this exact moment, they have no shared session key and absolutely zero mutual trust. They're literally just clearing their throats to say hello.
All right, so Taipei makes the very first move. We call this step the IK_init proposal. Taipei reaches out across the internet to say hello, but it's a very specific, highly technical hello. It proposes a strict set of security rules. It essentially says, hey, I want to use AES 256 for our encryption and SHA 256 to ensure our data's integrity. But it doesn't stop there. Along with those proposals, Taipei sends over its Diffie-Hellman group parameters, a public mathematical value, and a random number we call a nonce. Basically, it's laying its preferred security tools right out on the table for Taichung to evaluate. Now, what's really interesting about this slide is how it highlights that Diffie-Hellman concept we just mentioned, because it solves a mathematically mind-bending problem. It's the classic spy dilemma, right? How do you establish a shared secret over a compromised channel? How do Taipei and Taichung agree on a secret key when they know the entire internet could be watching, without actually sending the key itself over the internet? Because obviously, if you send your secret key out in the clear, the hackers grab it too, and your encryption is entirely worthless.
And here is the brilliant plot twist. The private value never leaves the device, yet both calculate the exact same shared secret. It's pure mathematical magic. Both Taipei and Taichung generate their own private values. Let's just call them A and B. They keep these perfectly hidden inside their own hardware. They only exchange their public values. By taking the other firewall's public value and running it through a complex formula with their own hidden private value, both firewalls independently calculate an identical shared secret. A bystander watching the public exchange simply cannot reverse engineer the math to find that secret. No way. So let's take a second to summarize the successful negotiation so far. By the end of this first IPsec init phase, Taipei and Taichung have confirmed the exact encryption algorithm they're both going to use. They've confirmed the integrity checks. Thanks to the magic of Diffie-Hellman, they have successfully generated shared IK session keys. And most importantly, they have established a protected, mathematically secure IK channel. Our diplomats have essentially built a temporary, completely soundproof room where they can finally whisper to each other without being overheard by the rest of the internet. But hold on, we aren't completely safe yet. I mean, we have a secure channel, but are you really who you say you are? We're now entering the second major hurdle, known as IK Oath Auth, because think about it. A beautifully encrypted, highly secure, soundproof room is totally useless to you if you've unknowingly built it with an imposter or a malicious hacker. Taipei needs rock-solid proof that it's talking to the actual, legitimate Taichung firewall and not some man in the middle. This is what I like to call the show me your badge moment. To prove their identities, enterprises typically use one of two methods. A pre-shared key, which is kind of like a long, complex password they both already know, or a digital certificate. Inside our secure channel, Taipei essentially says, all right, here is my official digital certificate proving my identity. Taichung takes a moment, verifies that certificate against a trusted authority, and replies, okay, your badge is real. You are indeed our trusted VPN peer. This verification happens in both directions until definitive mutual trust is completely established. And that brings us to a massive turning point in our explainer. Mutual trust is completely locked in. The management IPsec is officially complete. Now the diplomats step aside and they open the child essay. Also known as the IPsec essay, this child essay is the actual data channel. It's born from that secure management channel we just built, but its sole dedicated purpose is to serve as the VIP tunnel used exclusively to protect the real user data flowing between the two offices. The heavy lifting of the security detail has officially begun. And this brilliantly illustrates how we control the VIP list for that data tunnel using a traffic selector. The firewalls act just like strict bouncers at an exclusive club. The local traffic selector rule dictates that only traffic originating from the Taipei subnet 192.168.10.0/24 is allowed. The remote selector says it must be explicitly destined for the Taichung subnet 192.168.20.0/24. Only data packets matching these exact IP addresses are scooped up and pushed into the secure IPsec VPN tunnel. Everything else, ignored or turned away at the door. So the trust is established, the secure VIP tunnel is built, and our firewall bouncers have selected the exact traffic allowed inside. But that leaves us with one final, absolutely critical question to wrap up our explainer today. Now that the tunnel is completely ready, what does tunnel mode actually do to the physical packets? When that specific PC, sitting at 192.168.10.10, sends its private data toward Taichung, how does the firewall physically wrap, disguise, and encapsulate that data before throwing it onto the dangerous public internet? Well, that is a fascinating engineering marvel all its own, and it's the perfect topic for you to explore next based on this source material. Keep learning, keep questioning how things work under the hood, and I'll catch you in our next explainer.